All right. So I'll just so this is like so to get this isometry, basically it's like we do conformal mappings in 2 dimensions in our complex analysis. It's the same kind of thing. You just do a sequence of mappings. So what do you do? So first you take so we go the opposite direction. We'll go from the unit ball to the upper half plane. Okay. So from the unit ball, first we go to the ball of radius half by x goes to half x. Okay. Then we do a vertical translation. We move this up by x bar xn goes to x bar xn plus half. So now this is a ball of radius half, which is tangent to the horizontal plane here. Okay, it's lying in the upper half plane. Now I apply an inversion. Okay, so under an inversion, what will happen is that this ball here, this will go to an upper half plane of points with height at least 1. And then you just do a vertical translation by -1 to bring it down to the upper half plane. All right. So all you have to check is this step, that this ball goes to this upper half plane. So what is this ball? This ball is basically x bar comma xn minus 0 comma half. Norm is less than half, right? So if I take norm squared, then this becomes norm x bar squared plus xn minus half whole squared less than 1/4. So when I expand this out, I'll get norm x bar squared plus xn squared, that is norm x squared, minus xn plus 1/4, and that 1/4 will cancel with the 1/4 here. So this becomes norm x squared minus xn less than 0, right? And so this is equivalent to, I take this to the other side, xn over norm x squared bigger than 1. But xn over norm x squared, this is the nth coordinate of I of x, right? Yes? Right? This is the nth coordinate of I of x. I of x was x over norm x squared. So the nth coordinate is xn over norm x squared. So this is bigger than 1 if and only if you lie in this ball, right? So that means that this ball maps to this upper half space where the height is bigger than 1. Is this clear? Yes?
Yes, sir.
Okay, so we've constructed a sequence of mappings from here to here. Now all you have to check is that under these mappings, if I basically start to pull back the hyperbolic metric on the upper half space by these maps, so T2, then I pull back by I, then I pull back by T1, then I pull back by S, then I will get this metric on the disk. Okay, so that's a calculation you can do now. It's an easy calculation. Okay, so we have this map G, which is T2 composed with I, composed with T1, composed with S. And so now you pull back by each of these, right? So T2 star of G0 will be ds squared by xn minus 1 squared. Then we know what I star of this is. It will be I star of ds squared, that is ds squared over norm x to the 4 into I of this. So I of this will be basically xn over norm x squared minus 1 whole squared. So this becomes ds squared by xn minus x bar squared whole squared. And the other two pullbacks are just by translations and scalings. So that's an easy computation. And finally, you end up with this, okay? 4 ds squared by 1 minus norm x bar norm x squared whole squared. Is this okay? Yeah, so you can just check these other computations. All right, this one is easy. This is a translation. T2 is a translation. I star of ds squared, we know what it is. It's ds squared over norm x to the 4. And then you have this, basically an xn of I here, ix. So the nth coordinate of ix here, minus 1 whole square. And then this T1 is a translation and S is a scaling. So it's easy to check what happens to the metrics here. Is this all right? Yes?
Yes, sir.
Yes.
This is an easy computation right now. Okay, so we get this isometry. So what is the point? The point is this metric, you can see it is invariant under the orthogonal group of Rn, right? Yeah, because an orthogonal transformation preserves ds squared and it preserves norm x. Therefore, it's going to preserve this metric on the ball. Is this clear?
Yes, sir.
So, therefore,
Yes, sir.
orthogonal transformations, these are isometries of the ball fixing the origin. So, this will now tell us to finish today that Hn has constant sectional curvature, right? And so for that, we know that sectional curvature is preserved by isometries. So it's enough to show that the isometry group, it acts transitively on pairs of orthonormal tangent vectors, right? U1, U2. Is that clear? Then, I mean, it will act transitively on orthonormal, on two planes in the tangent spaces, right? Any two plane at any point, I can send to any other two plane at any other point, right? So first of all, I know that we act transitively on points, right? Yeah, so we work in the ball model. So we can send the base point of these two vectors, x naught, we can send it to the origin, right? And so then these two tangent vectors under the derivative of the isometry, they go to two orthonormal tangent vectors at the origin. Now you take these vectors v1, v2 at the origin, you extend them to an orthonormal basis, v1 to vn of Rn. Well, an orthonormal basis of the tangent space at Bn. Okay. And now you fix a standard basis E1 to En of the tangent space at the origin. And now we have an orthogonal transformation O in On, which maps VIs to EIs, right? So therefore, if I compose O with this T, then my U1, U2 at x naught get mapped to a fixed pair of orthonormal vectors E1, E2 at the origin, right? So therefore, I act transitively on pairs of orthonormal tangent vectors. Is this clear?
Yes, sir.
Okay.
Sir,
So therefore, the sectional curvature is constant. All right. Yes, question.
sir, do we know this isometry explicitly? This x not going to 0? No, right?
Yes, we know it explicitly, right? I mean, we have an explicit map from the
So
upper
we
half.
go back. We go to the upper half space. We
have a
move it.
scaling and translation here. We have
Yeah,
scaling
so
and translation, and then we conjugate it by this map. You'll get a map here.
okay. Yeah, yeah, okay, fine.
Right, yeah. But I mean, you can do it in a nicer way. If you want in a nicer way, what you can do is the following. I'll just tell you how to get this map.
I had seen once it is reflection to a with respect to a circle, sphere only. I mean, this composition of this type.
Right, right. So here's x naught, right? You take basically there'll be a hyperplane in Hn which in the ball. So this is a ball, right? This is a ball. This is higher dimensional now. You take the perpendicular bisector of these two. So the line joining the radius is a geodesic, like in the 2 dimensions. And then you take a sphere which is perpendicular to this and which is perpendicular to the boundary. So something like this. Okay.
Then just reflection with respect to that sphere.
And now you take reflection with respect to this sphere. Yeah. So that will send x naught to 0. Yeah. Well, you have to be a bit careful. This is a Euclidean reflection in the sphere. You have to check that x naught goes to 0. So that uses the fact that reflections in spheres perpendicular to the boundary are isometries. So if this is the perpendicular bisector, then this hyperbolic distance will be the same as the hyperbolic distance of the reflected point, and therefore x naught goes to 0. So yeah. I mean, you need to know that reflections in spheres perpendicular to the boundary are isometries of the hyperbolic metric on the disk, on the ball. That's all. Okay, let me stop here. Yeah, and so I'll see you next Thursday then, right? Tuesday is a holiday. Yes? Right?
Okay, sir.
Yes, yes.
Yeah, okay. So I'll see you next Thursday. Okay, bye-bye.